Hey guys, we're back. So let's talk about question 5 on week 4. Problem statements reads the following. 3 meter cube rigid tank contains hydrogen at pressure of 250 kilopascals and temperature of 550 Kelvin. Watch out with the Kelvin. Gas is now cooled until the temperature drops to 350. Determine the final pressure in the tank and the amount of heat transfer. All right, so now we're moving into ideal gases, right? So now this guy, hydrogen, is an ideal gas. And then we can put our hand to the sky and be grateful, because if it's an ideal gas, then PV equals nRT or MRT, depending on the format you use, is valid, right? What else happens if this is the situation? Well, if it's a rigid tank, delta V is 0, right? And if delta Z is 0, therefore the work done is going to be 0 here. What else? Well, if there's no mass coming in or out of this tank here, the other thing that we know is that the relationship P1 V1 T1 has to be valid as well, right? P1 V1 T1 has to be equal to P2 V2 T2. Why? Because, well, if you look at this equation here, if you isolate one of the sides, what remains if you send the T that way dividing, we're left with mass and the constant, ideal constant, or the number of moles in the ideal constant, right? So therefore, this makes our lives easier. Cool, so let's tackle this problem. Well, rigid tank, the volume, what do we know? State 1, let's put it down here. State 1 is P1 equals 250 kilopascals, T1 equals 550 Kelvin, and V1 we don't know. Oh, we do actually, because it's a 3 meter cube tank, right? We don't know the specific volume, but we do know the first volume. And then on state 2, what do we know about state 2? Well, we know the pressure or the temperature. No, temperature. No, P2 we don't know yet. T2 we know that it's 350 Kelvin, and we know that V1 equals V2 because there's no change in volume, right? So let's start by relating the things that we know in this guy here. Volumes are the same, they get cut off, so we can relate the pressures and the temperatures. We have both temperatures, we have one pressure, so we can find the other one, right? So my P2 will be equal to my P1 times my T2 divided by my T1. Okay, note that whatever unit you're using for temperature, as long as it's the same, is going to be cut off here, and we're left only with the units for the pressure, right? So whatever pressure we're using on this side is going to come out on the other side. So this guy here, so P2 is going to be 250 kilopascals times T2, 350 divided by 550, right? Again, kilopascals, Kelvin divided by Kelvin. Kelvin cuts Kelvin. We're left with kilopascals. Our P2 is, oops, I'm out of my screen. Sorry, guys. Apologies. So my P2 is 159.1 kilopascals, right? So we grab this off. Let's put this on over here. So this is 159.1 kilopascals. Brilliant. Brilliant. Let's go back to this here. Let me just put a little note to myself that this is my limit, so you don't cross it again. Okay, cool. All right, so we found the pressure. That's the first part of the question. So part A, yeah, we can call this part A. And now part B, we need to find Q, right? We need to find the heat. Right, now there's more than one way to do it. The easiest way is to relate the equation that you also should have learned this week, which is the equation that relates to mass, CV delta T. Okay, what's the CV? Why is it CV? Because there's no change in volume, right? The volume is the same, right? So the heating capacity when with the one volume, the same volume. Okay, and where can I find this? Well, if I go down to table A2 on page 899, I'll be able to grab the value for hydrogen, right? For a molecule of hydrogen. Now, there's something interesting here. Note that the CV is going to change with temperature, right? So for the initial temperature, we're going to have one CV, and the 350 we're going to have the different CV. Okay? So if we're going to grab it off the table, if we want to minimize our error, what we use is the bulk temperature, and we grab it off with the bulk temperature. Okay, so what is the bulk temperature? It's a mean temperature, right? The mean temperature, so bulk BT, bulk temperature, will be 550 Kelvin plus 350 Kelvin divided by 2. Yeah, that's 450. That's 900 divided by 2, 450. So I go to the table, this table here. I'll change colors. Where are the colors? Yeah. Yeah, so I go to this table and I look at 450, and I'm going to grab that CV equals 10.377 kilojoules per kilograms per Kelvin. Okay, so now plug and play, right? We need to, we have this delta T, it's the difference here. We have the CV. The only thing that we need to be able to finish this off is find the mass. And how can we find the mass? Precisely with this equation here, right? That's the only thing we're missing. I'm going to pause to change the sheet, and then we'll continue. All right, so continuing here, our quest to find the mass in this gas. All right, there's two options. I'm going to give you the easiest one. I'm pretty sure you're not going to like the other one. Our options are, we can use a general R, the constant, general constant, which is going to give us a number of moles, right? We can grab the number of moles with that constant. Or we can use a specific one for hydrogen and grab the mass straight off the bat. Okay, so if you go to the same table, same A2 table, the same page, 899, the property table, you're going to see that the R, specific R for hydrogen is 124 kilojoules per kilogram Kelvin. Yeah? So if you go straight to the R that already relates to mass, well, you can grab off this equation here as the mass. Your other option is to use a general R, which is the same for every single different gas, and then you're going to grab the number of moles, and then you have to relate to the periodic table to find the mass of your given situation. Up to you. They will render the same result. This one is last math, but it needs you guys to remember that this is going to change depending on your element or your molecule. Okay? How does this number come to be? Well, this is just a general gas constant related with the molecular weight for this given molecule, in this case hydrogen, right? Okay, so let's get to it. So if I want to find the mass, I'm going to solve for the mass. My mass will be my PV divided by RT. I can use either first state or second state because they have to be related, so you can choose. I'm going to do the first state, so 250 kilopascals. Volume, it's 3 meters cubed. Remember that this multiplication is going to render kilojoules, right? Then on the bottom here, 4.124 kilojoules, kilograms Kelvin, and times the temperature, which is for the first state 550 Kelvin. Okay, so Kelvin gets rid of Kelvin, kilojoules gets rid of kilojoules. Yep. So this is newtons over meter squared times meters cubed. That's going to be newtons times meters. Kilonewton meters is kilojoules. And then kilogram goes up, so this is going to be mass in kilograms. And this will be 0.33066 kilograms. Okay, and then we can go back to the equation that we were looking for, right? We're looking at for Q, right? Heat. And we found that heat is the mass times CV times delta T. So therefore, The heat in this process will be 0.33066 kilograms times CV that we grabbed, which was 10,377 kilojoules kilogram Kelvin. And the difference in temperature, this is my sheet out all that it does. So what is the difference in temperature? The final one is 350. The initial one is 550. My Q is 600 and... let me just show you guys units first. Kelvin, Kelvin, then kilogram, kilogram. We'll have it in kilojoules, which is energy units, which means we did a good job. I got 686.25 kilojoules. Okay? If you didn't use bulk temperature, if you got CV for the first state, for instance, you're going to have something similar, like 673. So watch out. It depends on what your assumptions are. You're going to have a slightly different value. This, in my opinion, is one of the best ones in terms of minimizing the errors that you can have while using the tables. Okay? This is negative because this guy is going to be a negative value. What this is telling us is that the initial state, which was 550, let's put it here, 550, and then the second state is 350. Yeah? So we're going from a state of high energy to a state of lower energy, and we're losing Q. That's what the negative is telling you. If you don't want to put a negative, you need to show us that you know the heat is leaving the system. Okay? Nothing hard in this question. Hope you guys understand it. Hit me up if you have questions. Talk soon.